Hello guys, it's the Caribbean Bookworm, and in this video I wanted to bring you guys something again new and special. And our universe consists out of a lot of mysterious and funky objects, both on the macroscopic and gigantic scales as well as on the microscopic and very small scale. Well, in this video, we will be looking at one of those objects on the macroscopic and gigantic scales. And yes, I said we as to not just referring to me and you, but also referring to a third party which who has gladfully decided to collaborate with me in this fun little video. And that is the YouTuber My Hubble Abode. She's a very nice YouTuber and a graduate student in the UK studying astrophysics. And her channel has a bunch of cool videos, such as her most recent video on the concept of dark matter and how the theoretical formalism of dark matter came to be, as well as some very interesting observational facts as to how astronomers came to accept that dark matter is a thing, such as one of my favorites being that which she mentioned of the bullet cluster, which I didn't know about, but basically where you had two clusters of galaxies and one of them shooting through the other, literally like a bullet, and you can see actually these dark matter halos still hanging around despite the one galaxy cluster shooting through the other. Like it can be seen through like micro lensing effects and such, and it's super fascinating stuff. I highly recommend you check that video out by her, as well as some of her other videos. She has a really interesting video on the cosmological structures that our universe can have, and she combines basically her knowledge of astronomy and astrophysics with her passion for crocheting, which makes for a very interesting and unique mix. And also there are two hilarious videos on like physics slanders, which you should definitely check out. So later on, My Hubble Abode, she will be talking about a particular point in our video, and I will start by talking about the first point in our video. So in essence, we will be talking, the mysterious object in question is black holes. So we will be doing a 1 pound black hole versus a 1,000 pound black hole. I mean, both of them are black holes, but you can have different packaging. So we will see the cheaper package first, and then the more expensive and niche package, which actually might be the most abundant package in our universe, but we will get to that. So the 1 pound black hole will actually be a black hole that is not rotating around its axis, and it's called a Schwarzschild black hole, as it is not rotating around its axis and it doesn't have a charge either. And the black hole, which is the 1,000 pound black hole, which My Hubble Abode will be talking about, is a so-called Kerr black hole, which is actually rotating around its axis. So without further ado, let's actually get into the 1 pound black hole. Before starting and jumping immediately into black holes, I just want to give a quick little bit of history as to how this concept of black holes came to be. And in essence, this idea of black holes, despite being very popular in like pop media and like movies right now, such as Interstellar or Rick and Morty and such, the concept is itself is actually very old. The idea came just a couple of decades after the passing of Isaac Newton in the late 1700s, you can say, and it was proposed by this country parson and polymath by the name of John Mitchell. He was British and worked for a time at Cambridge, as did a lot of famous names in astronomy and physics, apparently. And he basically proposed this idea that if you have a celestial body that has an escape velocity that is greater than that of light, then you would have a body that does not emit any type of light, that would in essence be invisible. And he thought of that maybe you can have stars which have such a high amount of mass, or perhaps such a particular high amount of density, that the escape velocity for this thing might be bigger than that of light. And you would have something that is invisible, that you cannot even see, because the light from its surface cannot even escape its surface in order to actually reach you, the observer's eyes. So this is what he coined a dark star, and of course it wasn't very mathematically and rigorously built. That took the likes of Albert Einstein, but the concept of that is basically still what we think of as black holes in essence. So in order to drive this point home and actually make it a very solid theory and concept, enter Albert Einstein. Albert Einstein basically, after publishing his special theory of relativity, took him 10 years to come up with a more general theory of relativity, which actually was able to describe what gravity itself was. In essence, Einstein's general theory of relativity describes this so-called space-time in a manner that is very consistent, and actually that describes gravity itself as a geometric thing. So in order to unpack that, basically the special theory of relativity is a theory of reference frame. So if you have one guy, for example, standing outside right now in just a field, and you have another guy sitting in the train, and if the train is moving with a constant velocity, then both people are in what is known as an inertial frame of reference. So the laws of physics for both the person standing outside and the person moving in the train should be the same. Now, this combined with the fact that the speed of light should appear to be at the same velocity regardless of which reference frame you're looking at it from. These two things led to some very interesting things and notions in the laws of physics that were not very clear beforehand with Newton's laws. So you get weird effects like time dilation and length contractions as things go closer to the speed of light. But the key thing is that special relativity looked at things from inertial frames of reference, and we know that a lot of time in the universe, almost all, you could say, like reference frames are accelerating to one degree or another. So in order to describe like the point of view of things which experience a type of acceleration of some sort, then you needed this more powerful and more general theory of relativity. And that is exactly what Einstein did. He came up at the end of the day with this very powerful and scary equation known as the Einstein field equations, which in general I think it's about 16 equations condensed into these two like expressions on these two sides right here. But in general, it says that the matter energy content in the universe tells space-time how it should curve. It tells you that on one end, and on the other end, it tells you that the curvature of space-time dictates how this energy mass content in the universe should move, basically. And things in the universe tend to travel, well, the straightest possible path you can have in a given coordinate system. So this is where this geometric picture of general relativity comes into play. That if you have a given coordinate system, then or a given like frame, you could say, then the path which an object travels in that frame is dictated by this Einstein field equation, and this it will be the straightest possible path. It is what is called in jargon the geodesic. But the path of this geodesic doesn't necessarily have to be a straight line. Actually, when you have curvature of space-time, because of this like curvature of space-time due to, for example, something that is very massive, you can have that basically something moving through space-time will naturally follow a geodesic that is a curved path. And as a matter of fact, that is the reason why, for example, light can be affected by gravity despite not having mass in it of itself. This does not make any sense in the Newtonian sense of gravity, but it does in this more like Einstein sense of gravity, in which things tend to follow geodesics in space-time. So with that in mind, the Einstein field equations do have some like exact solutions, but these equations are known to be very painfully hard for theorists to solve. So there is a very finite and small set of exact solutions for the Einstein field equations. But one of them did come exactly or almost exactly 1 year after Einstein published his theory to begin with. And it was done by this German astronomer and physicist by the name of Karl Schwarzschild. Basically, I think he wanted to distract himself like throughout World War I or something. So he did some physics, as you always would, to distract yourself. And he came up with a solution for the Einstein field equation, which gave rise to this thing called the Schwarzschild metric. Again, a lot of expression, a lot of terms, but we're getting there. The Schwarzschild metric, in essence, describes a coordinate system at which, well, Schwarzschild himself assumed a particular mathematical thing. He assumed something known as spherical symmetry. And for that reason, the metric which he found as the solution to Einstein's equations was actually described in something known as spherical coordinates, which if you're a physics student, you might have seen a lot, but don't stress about the detail. In essence, the R stands for a given radius of a spherical thing. The theta stands for an angular deviation, but an angular deviation as, say, if you have an xy axis and a z axis, the angular deviation right here would be a theta, and phi stands for an angular deviation on the xy plane itself. If you have this Schwarzschild metric, you can see some things happening right here. This ds squared is just a mathematical way of saying that the smallest distance you can travel is actually ds squared. You can kind of think of it in the Pythagorean sense of things, that if I have an xy coordinate system and if I have a random curve on this coordinate system, then the smallest increment on that curve is what I will call ds. And basically this ds, I can think of it as being a line segment of a triangle, at which this ds is like the hypotenuse of the triangle. So ds squared then will be actually the small deviation in dx and a small deviation in dy, well, both of them squared. So ds squared is ds squared, that small infinitesimal step on the curve, is actually dx squared plus dy squared. So ds will be the square root of that. With the idea of the metric now, we can look at the expression for the Schwarzschild metric. We can notice some interesting things. We can notice that, for example, there is this r subscript s like term or like little thing right in there. And that r subscript s is something denoted as the Schwarzschild radius. The Schwarzschild radius is a radius at which, if basically you have something that obtains the Schwarzschild radius or a radius smaller than that, then basically it curves space-time so much that all of the geodesics will point inwards in such a manner that not even light will be able to technically escape the gravitational pull of said object. This in essence gives a mathematically more rigorous definition for what at the end of the day is the same thing which John Mitchell wanted to describe, basically a black hole instead of a dark star. And this isn't the only weird oddity that you can have from this Schwarzschild metric. Actually, if we look at the expression closer and if we clean up some things by, for example, stating that you want to use natural units, in which you can say that the speed of light is just equal to 1. Yes, physicists can technically do that. It's legal. You just rearrange things with units. But if you do that, you can see an expression that looks somewhat like this. And this is something that you can find in a lot of like textbook and literature. But this is something that I took off of Sean Carroll's notes on general relativity, which are really good. But in essence, what you need to look here is basically they substituted for RS the expression which you have for what the Schwarzschild metric actually stands for, and you get this thing which is written right here. And this tells you that if, for example, the radius that you have in your given metric tends to infinity, then you have something that basically boils down to your regular metric that you would get in otherwise flat space, in what one will call otherwise the Minkowski metric, which is the metric which basically is like still holds for special relativity. But if r actually becomes smaller and smaller, and especially if it tends to 0, then you get something peculiar. Then you have that basically if the r approaches 0, you have something that is kind of undefined. Because you're dividing in a lot of cases by 0 right there, and that just screams infinity. So if, say, you were to divide by 0, then you will get like something that is 1 minus like infinity. That's kind of ugly. You would get minus infinity with a minus in front plus infinity. Things go to infinity basically. And this tells you that at r equals 0, you have this spot of infinite curvature, which is known as a space-time singularity. And it's not only for black holes very prominent, but it can also show up depending on your mathematical description of the universe at the origin of the universe. But for that, I'd highly encourage you to check out again my Hubble's Abode video on the cosmological shapes of the universe. And the space-time singularity was thought to be a mathematical oddity and something that people weren't quite really comfortable with for a long period of time until the mid-60s, where the British physicist Roger Penrose wrote a detailed paper, very short paper but very concise one, on what the implications of space-time singularities are for general relativity. And he thought of these things to be like, oh, they might actually have physical meaning of some sort. So Roger Penrose stated that, okay, well, maybe these space-time singularities are a thing that you can use for the description of black holes. And I mean, he got a Nobel Prize for this in 2020 for his 1965 paper, which you can find almost anywhere online. And on top of that, he even postulated something which is still somewhat debated amongst a lot of physicists, and that is something that is known as the cosmic censorship hypothesis. The cosmic censorship hypothesis basically states that because you have this space-time singularity, something tending to infinity, well, nature shouldn't really like infinities, so the idea why maybe this thing exists is because it is isolated from our universe, from our just regular space-time, by this boundary region that is, well, the event horizon of the black hole, or that is basically the Schwarzschild radius. So in essence, this pretty much captures a lot of the properties of a Schwarzschild black hole. So you have something that can come to be, for example, due to the collapse of a star. Say if you had a star that wasn't rotating around its axis, maybe the thing goes supernova, and you have that the inner core of the star collapses so much beyond something that is known as the Tolman-Oppenheimer-Volkoff, I think, or the TOV limit. And if something compresses beyond this limit, then it becomes much more compact than a neutron star, which is one of the most dense astronomical objects that we know of. So if this thing goes beyond the TOV limit, then it can collapse immediately almost into a black hole. So that can happen maybe through to a supernova, shedding the outer bits of the star and the inner core collapsing, or the star itself can collapse pretty much directly to a black hole. And this is pretty interesting. It can explain basically how you can have these monstrous and mysterious creatures of physics out there in our actual universe, and that's what people tend to exactly find. But that's a lot of information on black holes, and technically, because of the fact that almost everything in the universe is kind of moving and rotating to a lot of degree, very likely Schwarzschild black holes do not technically exist out there, because a lot of the things, or a lot of the hypothesized mechanisms for how black holes can form, well, a lot of them basically entail that the thing which makes the black hole or causes something to be a black hole probably contains a little bit of angular momentum. So the black hole that you will get is one that is actually rotating, because, for example, if you have a star that is going to collapse into a black hole directly, the thing was probably rotating around its axis to at least some bit. So if it collapses, and especially as the radius actually decreases, to conserve angular momentum, it actually is going to maintain this rotation or this spin. And the main reason why a lot of physicists think that black holes contain something like spin, mass, and charge, and not much else, is due to a little bit of thing known as the no-hair theorem for black holes. So that was a lot of jargon and nomenclature, so I hope you were able to follow still. But in essence, I'm no longer curious about this 1-pound black hole. We want to now dive into those black holes which do contain angular momentum. So without further ado, take it away, my Hubble Abode.
Thank you very much, Nazir. And now let's get on to our 1,000-pound black holes. The Kerr black hole adds one very small addition to the Schwarzschild black hole, and that is rotation. And you'd think it wouldn't make that big of an impact, right? I mean, when we look at orbits such as the Sun and the Earth, we don't actually care about the rotation of the Sun all that much. But when it comes to black holes, we're playing a completely different game. So there are 4 types of black hole maths, depending on whether there's mass and charge, mass and spin, or all 3. These all have gravitational descriptions which are exact solutions from the Einstein field equations. Black holes that just rotate and have mass are described by the Kerr metric, which I've written over here to scare you, but don't worry, we don't need to go into it in much detail. Although one thing that those who know the horrors will have already recognised, hopefully, is that it doesn't describe a spherical object, but in fact an ellipsoid. Plotting spheres is actually fairly easy. If you have an x and y, so Cartesian coordinates, you can use those two by Pythagoras' theorem to make a radius, and then with an angle you can spin that radius around and create a circle. With a second angle you can actually create a sphere. With ellipsoid you do need to fiddle around with the angles a bit more to actually elongate the sphere into an ellipse, which we can actually see in the Kerr metric itself. But here you can actually see a really interesting term which seems a little bit random at first. This is actually a more simplified way to describe the angular momentum over the mass and the speed of light, with the angular momentum essentially being your rotation. So what this is actually telling us is that the curvature of space-time around this black hole when it's very close actually is sort of distorted with the rotation, and on its own that's actually quite hard to visualize. Probably almost everyone and their cat has seen this image of space-time curving around a very dense mass like a black hole, right? Well, this is actually a fairly good representation or a visualization of a non-rotating black hole, so a Schwarzschild black hole. Like we said with the Kerr metric, around this black hole there's going to be some distortion that actually distorts with the angular momentum and the rotation of the black hole. So our diagram should actually look a little bit more like this. And from that we can actually get the Schwarzschild black hole back. So if you set that angular momentum to 0, that distortion becomes 0 and you go back to the original visualization. This very interesting swirly distortion is an effect called frame dragging, and it's where you're rotating with the black hole as you get very close to it. The area where you rotate is called the ergosphere, and it lies just outside the outer event horizon. And as the black hole becomes more and more fast with its rotation, so it starts to spin more, this ergosphere actually becomes more oblate and it starts to look a little bit like a squash. What's interesting about the ergosphere is that because it's not actually within the outer event horizon itself, particles can actually escape. And so what we expect might happen is that through the Penrose process, these particles can escape and take away a little bit of energy from the black hole, essentially slowing it down until it stops rotating. The Kerr metric doesn't just describe an outer event horizon, the one that we all know and love and we learn about in classes as the event horizon where light cannot escape. There's also other horizons which are described by the mathematics, such as the inner event horizon. Now, for Kerr black holes, the inner horizon is actually a Cauchy horizon. And here, this is where time actually starts to break down and get really weird. And we can get things called closed time-like curves, where it's essentially like time travel, where you can sort of move into your own past, cause may not have an effect. Very interesting things which come out of the mathematics, and yet we don't actually really have a good understanding of how these things work. Now, with the basic Schwarzschild non-rotating black hole, the mathematics shows us that we expect a perfectly spherical black hole with just a point singularity that's infinitely small in the center of it. But what's interesting about Kerr black holes is that because it rotates, it actually is somewhat squashed, a bit similar to how stars become more oblate with their increasing angular momentum. But what's very, very cool about this is that their singularities no longer become points, but infinitely small rings, essentially. And this has a great effect on the black hole, in fact, because it essentially squashes it down and makes it more oblate. Very similar to how stars actually become more oblate and squashed, and planets do with their increasing angular momentum. Unfortunately, because we can never actually go inside a black hole, come out and tell the story and describe what we actually saw, we can never really find out what these mathematical descriptions actually look like in real life. The next step on the black hole ladder, I guess the 1001 pound black hole, is the Kerr-Newman black hole, which not only has mass, rotation, but it also has charge, so it has all three features that a black hole can have. The thing about charge when it comes to black holes is that they don't really have any. The thing about particles is that they tend to like to neutralize each other, so opposite charges of particles will like to attract each other. and this actually produces an overall net neutral charge on the black hole. Another thing about the maths behind the Kerr-Newman black hole, so the Kerr-Newman metric, is that it is very, very incomplete. So that's going to be a job for you future physicists, so you better get back to your studies. Anyways, thank you very much for listening to both of us, and a very special thank you to the Caribbean Bookworm for not only the collaboration, but just letting me on his channel to do some very cool black hole science. I highly suggest, if you're into physics and maths, do him a favour and hit subscribe on his channel, and you will definitely not be disappointed. Also, feel free to have a look at my channel and subscribe too if you like. With that being said, I'll see you soon.
Thank you so much for giving us a tour through this wonderful and interesting world of curved black holes, my Hubble Abode. And as you guys might have already noticed, curved black holes are even more complicated than short-shield ones, but they're more interesting because very likely astrophysical stuff out there probably collapsed or merged down to these curved black holes instead of this very static, non-rotating short-shield black holes. But nevertheless, you can use both metrics, you could say, to still study interesting properties about black holes. To some extent, you can approximate things to be a short-shield black holes, especially if, say, their angular momentum might be ridiculously small. But very likely you'd want to, especially if you want to have the highest precision with a particular research in mind and such, you'd want to use the Kerr metric for particular types of black holes. And it is what researchers are actively doing right now out there in the field. But I hope in general you got some idea of both this package of the 1 pound black hole and the more fancier package of the 1,000 pound black hole, because like a guitar in which you're deciding to buy a $50 guitar or a $5,000 guitar, I mean, that's all in the details basically, but at the end of the day they both produce music. At the end of the day, two black holes are still very mysterious things out there in our universe and kind of peer through the depths and like edges, you could say, of our modern areas of physics. So I hope you're able to find this video fascinating and interesting, and thank you again to my Hubble Abode for participating and collaborating in this video. I'm eager and curious to see more content on your channel as well. And of course, as for you guys, the general viewers, I hope you guys stay tuned to see more of both me and of my Hubble Abode, as well as both here and there you'll find some nice content on astronomy and physics. So I hope you stay tuned. Thank you again for watching this video, especially if you stuck all the way through. Feel free to leave a like and subscribe to both our channels, to me and my Hubble Abode. Leave a comment if you found this interesting, and if you want to see something specific, let us know down below. And I hope to see you guys again very soon. Take care and bye.